Now that we have the 8x8 blocks for each one of the planes the YCbC are, we are ready to go into the forward transform. So the first thing we need to understand is, why are we going to do a forward transform? Let's just explain first of all, how do we measure the error that we create in images when we are doing compression, if we are doing a lossy compression? And the basic idea is that error is measured with what's called the mean square error, MSE, or mean square error. And it's computed as following. The mean square error, the MSE, is equal to 1 over the number of pixels. That's just a normalization. We sum over all the pixels. And what we do is we basically compute the square of the error. We're going to have the reconstructed image, let's call it F, reconstructed, minus the original image, square. We go over every single pixel, so we're going to do F. So let's say that the original F was 100 and we reconstructed 98. So we have the difference is 2, we square it, is 4. And we do that for every single pixel. We sum that, we normalize that by the number of pixels. And most of the time, because we have square here, we take a square root there. So it's called the root mean square error. That's how we measure the error. Now, why are we going to do a transform? Let's imagine that we take, remember, we're talking n by n blocks now. In general, we're talking 8 by 8, but we're talking n by n. So we have n by n pixels because we're working on each one of the blocks independently. Imagine that although these are n by n 64 pixels, I want to transmit only one. I'm going to just give you the option to transmit only one of them. So if we take just a regular image and we transmit only one, we're going to get a tremendous error. But we might be able to do a transform into a different 8 by 8. The transform has to be reversible. I should be able to go back. And we do this transform, we have new 8 by 8, and maybe in that transform domain, we can take only the first one and still do a reasonable job. It turns out that there is a transform that allows us to do that, and that's called the Karhunen-Loew transform. That transform has something very particular. You go into that transform domain. I'm going to write down in a second what do I mean by a transform, but think it's nothing else than a multiplication by a matrix. Nothing else than that. So I have my 8 by 8. I do something, I go into a new 8 by 8 block or 8 by 8 image. And then if what I did is a Karhunen-Loew transform, that's also sometimes written as KLT, Karhunen-Loew transform. If I'm in that domain, if I take the first of those, just the first out of the 64, and I compute the mean square error, remember, I basically did a reconstruction with only one. So I take my image, I do a Karhunen-Loew transform, I remove 63 of the coefficients, I come back and I compute the mean square error. I got the smallest possible mean square error I could have gotten with only one basically coefficient, just transmitting only one. If I want 3, I can do actually exactly the same. And the interesting part with the Karhunen-Loew transform is not only that with 1 I get the best error, but actually that one is the first one. So you have 64, you go into a new 64, you pick the first one. That's the best you can do if you're only allowed to use one coefficient. If you're allowed to use 3, you pick the first 3. So it's a great transform, but it has only one major problem. The problem of this transform is that it's image dependent. I don't know how to do it. So I told you it's going to be a matrix multiplication, but I don't know the coefficients of the matrix until I don't see the image. You give me the image, or you give me some information about the image, then I will be able to compute the coefficients of that matrix. And that's not very practical. It's very slow, and also I cannot do things on the fly as things come. So to replace that will come what's called the discrete cosine transform, which is what is actually used in JPEG. So let's just write down the equations for the discrete cosine transform, and we are going to understand a bit more of what a transform is. But let's keep in our minds that what we actually want is a Karhunen-Loew transform. What the Karhunen-Loew is doing is decorrelating the image. It's putting a lot of information in the first coefficient and a bit more of information in the second, which is independent of the first, and so on, in such a way that if we want to compute the mean square error, we are optimal. But we're going to be suboptimal with the discrete cosine transform, but it's going to have a fixed matrix, fixed coefficient, so it's universal. We're going to be able to use it for every image without having to recompute it. So what is a transform? The idea is very simple. We have an image, and we can call this image, let's say, fxy, and this is the transform. We're going to go into a new domain, T, U, V. Okay? And those of you that are familiar with Fourier is one of the transform. So we're going to sum over all the pixels in our image. Remember, we basically have n. So we're going to go from 0 to n minus 1. We're going to go from 0 to n minus 1. And we are going to take our image f and multiply by transform coefficients. This is what will become, I have to give you the formulas for what are these numbers for DCT, for the discrete cosine transform. This will be completely image dependent for the Karhunen-Loew. Will not only depend on the positions you are, it will actually depend on the actual gray values, on the actual statistics of your image. So this is a transform. I sum over x and y, which means that x and y will basically disappear after my summation, and I get a new image, which is again 8 by 8 or n by n. So this is n by n, and it's just in a transform domain. And you can write this in matrix notation. Now, of course, a transform is only useful if you actually can invert it. It won't be very nice that you give me an image, I go into a transform domain, that then visually I don't understand what's going on there. So there's also an inverse formula, so I can get back f x, y. It will be the sum from u equals 0 to n minus 1, the sum from v equals 0 to n minus 1 of now my transform coefficients, t, u, v, and then the inverse of the transform, which we are going to write, sometimes it's equal to r, sometimes it's not, x, y, u, v. So I take an image, I do this operation, I get a new image in a transform domain, and then I go and invert it. That's a transform. So to specify the transform, I basically have to tell you what are these guys, what's R and what's S. And once again, it's not hard to see, and you can just do this as an optional homework to write this in a matrix notation. It's not hard at all. So I need to specify these two guys, these two functions, R and S, which, as I say, ideally to minimize the mean square error to be optimal, we would like it to be the Karhunen-Loew transform, but we can't. So we're going to use the DCT, which I'm going to write next. So what's the DCT? In the DCT, R, X, Y, U, and V is actually equal to S, X, Y, U, and V. And this is actually equal to some normalization coefficients, alpha U, alpha V, Oh, this V and this V are the same. I apologize for just writing two different V's. Cosine of the following 2 times x plus 1 u pi over 2 times n, this is the size, times cosine, exactly the same but for the other coordinate, 2y plus 1 v pi over 2n. That's the general formulation, and I have to basically write for you what's this. It's just a normalization. It's very common in this type of transforms. That's the square root of 1 over n for u equals 0, and the square root of 2 over n for u different than 0. So here it is. I just gave you the formulas for DCT, or the discrete cosine transform. Those that are familiar with Fourier, this is basically the real part of a Fourier transform. It's almost that part. So once again, the forward transform and the backwards transform are exactly the same formulas. Very nice, because you need to build one piece of software or one piece of hardware to do both the forward and the backward. And then it's just a cosine transform. Okay, so it's the cosine here and the cosine here, and these are just normalization coefficients. This is the discrete cosine transform. Okay, let's just see it. What I want to see, I want to show you these functions. These are the matrices that will multiply your image, as we have seen in the previous slide, in order to get the transform. So here you see, actually, in this case, just to make our illustration easy, we use n equal 4. So these are each one of the bases. If I go back to the formulas and basically I put u equals 0, v equals 0, I get a cosine, which is a function of only x and y. The formulas were functions of u, v, x, and y. But now I fix u and v, I make both of them equal 0, I get a formula of x and y. I get actually a 4x4 image, which will be this. If I basically fix v equal 1 and u equals 0, I get this, and so on. So basically, these r and s are nothing else than what's called basis functions. And what we're trying to do is we're trying to decompose our small n by n image into the linear combination of these basis functions. So if your image is flat, it's going to have your t, u, v. It's going to only be non-zero for this. If your image has a lot of variations, you're going to have coefficients also for t, 3, 3. So each one of the t, u, v's tells you how much of this type of component you have. Okay? So basically, you have represented your n by n image into a linear combination of these type of images. The important part is that these images are constant. Again, in the Karunian Loew, they won't be. And that's very difficult to have a very efficient hardware implementation to be able to do that in real time. Here, this basis is fixed. You give me an image, I'm going to represent it as a linear combination of these bases. And t, u, v tells me how much of each one of these I have in my image, in my tiny n by n image. So that's a transform. Basically, nothing else than going into coefficients that tell us how much of each one of these components. So I decompose my image into these components, which are kind of frequency components. You see that there is more variation as I increase v and as I increase u in the vertical or horizontal direction. There's one thing I haven't told you. I say, okay, I can't do a Karhunen-Loew transform. I cannot compute basis for a Karhunen-Loew because it's too expensive. Then I go and do a discrete cosine transform. Why a discrete cosine transform? Why not a Fourier transform or any other transform, a Hadamard transform? There are many transforms out there. So there is a couple of reasons why we use the DCT. One of them is that although I want to do a Karhunen-Loew transform, I need to do a DCT. It turns out that the DCT is, for particular cases, actually exactly equal to the Karhunen-Loew transform. Those particular cases are when the image is what's called Markovian. So a pixel depends basically on the pixel next to it in a very particular form, and again the pixel next to the pixel next to it. So those are images that are called Markovian. So if you assume something about your image, you can show that the Karhunen-Loew transform ends up being the DCT. So at the end, it is a constant basis like we see here. That's one reason, and to basically decide to use the DCT. The other reason that we use the DCT is because of the following. Remember that I'm working from the whole image. I'm basically having n by n blocks. Okay? So one may wonder why not to use, for example, a Fourier transform. If we go back into the theory of Fourier transform, when you do a discrete Fourier transform, you're making an underlying assumption of periodicity. So you're basically assuming that your image repeats itself, as we can see here. So this comes back here, and this comes back here. Okay? So there is a repetition of your image. That's the underlying mathematical assumption to be able to formally do a Fourier transform of this 8x8 block. And here I'm drawing just one line of the 8x8 block, but the same assumption basically goes in the other direction and then in the two-dimensional. Now, this basically means that when your block ends, you're expecting the pixel in the next block to basically be identical to the pixel that it was here. Okay, so you expect this block to basically repeat here and repeats here. That's your underlying assumption. It's not very probable that the pixel that was here is the same pixel value that was here. Not even close in an 8x8 block, maybe. On the other hand, DCT assumes a different type of periodicity. Basically, DCT assumes that at the boundary, you have mirror symmetry. So basically, your image basically repeats, but it kind of falls. So the assumption says, okay, I'm assuming that the pixel here is similar to the pixel here, right next to it. Not that the pixel is identical to the one that comes 8 pixels later, but just the pixel right next to it. And that's a much more reasonable assumption. So those are the two of the main reasons why we use the DCT. One is because for certain types of images, the DCT is the Karhunen-Loew. The other is because the periodicity, the type of periodicity assumption, is much more applicable to images where we started by these n by n or 8x8 blocks. So now we have the DCT. We started with an image, we divided n by n blocks, we do a transform into a discrete cosine transform where every coefficient tells us how much of this basis are we using. I keep talking about 8x8. How we came to 8x8, actually there was a lot of studies before JPEG was defined to get to 8x8, but let me just illustrate what happens here. This is an image that basically we took the whole image. In this case, we don't divide. This is already a block of that image, Lina, that we talked before. We did a discrete cosine transform of this entire block, and we took 25% of the coefficients. So we took basically only 1/4 of the coefficients and we made everybody else 0, and then we did the inverse. And that's the result that we got. We have introduced error. And remember, basically, the DCT is what's going to try to do. It's going to try to bring us into a domain that introducing error, basically killing some of the coefficients, making them 0 or making errors on them, won't be as noticeable. But in this case, we did it very simple. We just took 25% of the DCT coefficients. Which ones is going to be very clear soon, but just imagine that we took the 1/4 of the basically largest coefficients. Now, first we did it for the whole image. Here we actually took only 2x2 blocks. So we went here and we did divided in 2x2 blocks, and we did a DCT of every 2x2, and we took 25%. So we basically ended with only 1, and we came back. And you see this very, very annoying blocking artifact. Then we did the same for 4x4, and we did the same for 8x8. And we see that basically it gets better and better. So you might wonder, okay, 2x2 is too little, but why to stop at 8x8? Why not to go to 16x16 and 32x32? And why not to just do the DCT for the entire image? There's a couple of reasons for that. One is computational. Basically, it's cheaper to do multiple small DCTs than one large DCT. So if you have let's say a 16x16 image, I'd rather do 4 8x8 DCTs than doing just one 16x16 DCT. That's one of the reasons. Another reason is this magic approximation of DCT to the Karhunen-Loew. I say that happens under certain conditions, a Markovian condition. If you're in a small region at 8x8 block, that condition, that Markovian condition, will probably apply. But if you're on a very large image, the whole image won't have a Markovian condition. So basically in small regions, you expect that assumption to hold, but it doesn't hold in large regions. And it's not hard to see that. If you're just, let's say, looking at me right now, you see that there is a lot of correlation here, more or less the same gray values. But if you actually start moving away and you say, is there a correlation between the pixel value here and the pixel value here, that they're very far away? There's actually no correlation. I can actually change my shirt and without prior information. So there is no correlation. When you get far away in your image, pixels that are far away, basically they start being decorrelated. So you need to get to a compromise. On one side, you want very small blocks because you want to be computationally very efficient. On the other hand, basically, you don't want too small blocks because you get into this problem of not having enough information in the block, enough correlation to be able to decorrelate with the transform. And if you get to too large blocks, you start paying computations and you start paying that you violated the assumptions for which the DCT is good. So 8x8 is a good compromise that I say was significantly studied, and it got into a very, very good compromise. And that's what's used today for JPEG. So to conclude this part of the DCT, I just want to show you once again this image Lina. And these are just two different cases, but don't worry about that for the moment. Here, basically, we took 8x8 blocks, we did a DCT, and we kept 12.5% of the coefficients, and then we came back. Not really quantization, which is going to be our next step, just a DCT and the inverse DCT. And it looks pretty good. That means it's just, when we just look for the first time at the image, we actually have achieved compression because we only kept 12.5% of the pixels. And we got an image which looks almost identical to the original one. And that's because we did that in the DCT domain. If we were to actually throw basically a lot of pixels here and keep only 12.5%, we will not be able to get this quality of the image. This is just the error between the original and the reconstructed. And as you see, it's relatively small error. So this is pretty good compression by nothing else than doing a DCT, basically removing a lot of the coefficients and coming back. So now we have the front end and we have the back end. What's missing is the middle. I'm in the DCT domain. Can I achieve even more compression by doing quantization in a smart fashion? And that's going to be the subject of our next video clip.